Okay, so today I wanted to look at another averaging style problem. And this time we're talking about a projectile launched with the usual parameters, so some initial speed v0 at some initial angle theta. It'll follow its usual trajectory. But I want to know, what is the average speed of this projectile between its launch point and its vertex or apex? And this problem is actually a little bit ambiguously worded. I know how we're supposed to interpret it, but there's actually a couple different ways you could think about this problem. And I want to talk about those differences and why we should be very careful when we're averaging things. So first off, average with respect to what? And that's usually the problem when you say the word average. The speed is going to depend on a lot of things. It's going to depend on, you could say it depends on time, parametrically. That's probably the most natural way to interpret this. But you could also ask about the average as a function of height, or the average as a function of horizontal position. So there's many different ways to average this. I'm going to interpret this as meaning the average over time, but we could do the same problem and find a different answer if we try to calculate the average over, say, vertical or horizontal position. Okay, so that's the first thing. The second thing that can go wrong is a mistake, not just a misinterpretation, when we're trying to find the average speed. I'm going to use the notation angle brackets when we're talking about average speed. And I think that many people, when they're first approaching averaging, especially something to do with the vector, so speed is the magnitude of a vector quantity, would be to think, oh, I know what I'll do. I'll find the average velocity, and then I'll take its magnitude. So the thing is, there are a couple other versions of a question that could be posed that are very similar but not quite the same. For example, this is not the same thing as saying I'm going to find the magnitude of the average velocity. These are not the same. In fact, this, if we wanted to write it out, is the average of the magnitude of the velocity, which is not the same as the magnitude of the average velocity. Now, we could go calculate these separately and we'll find different answers, but it's important to note, well, you can't mix and match those things around. This is related to the fact that the average of a square is not equal to the square of the average in general. In fact, we might be relating something like this to the RMS velocity. So if I'm trying to find the root mean square, the square root of the average of the squared components, which is what would come up with the Pythagorean theorem type thing, you might think, oh, that's what I'll use to find this, and actually that won't work. So let's actually start our problem by finding that instead, just to mix it up a little bit. Let's calculate the RMS speed. So this really does mean the square root of the average of the squares, or sum of the squares. So in our case, the magnitude of the velocity squared is going to be vx squared plus vy squared from Pythagoras. Let's average those and then take the square root, which notice is not the same thing as this. I'll put a little reminder. These are not the same. But let's calculate this one first, just so we have something to compare. Let's also recall off to the side that we already know what these are as functions of time. So all of these averages will be time averages. So I'll put a little t on these to remind us we're looking for time averages. Okay, so here are the usual velocity components for a projectile. And now let's just square them and see what an average is. We should also remember, like, how do we actually find an average? I'm not doing a discrete average where I add things up and divide by a total. So anytime we're talking about an average of some function, let's say it's a function of x, and we're thinking of an average with respect to x, it's going to have to involve some sort of interval, let's say from a to b. We'll add up the function values, which really just means integrate over that range. And then we'll divide by the total length of that interval. That's what gives us the average. It's still a sum divided by total, but now it's really an integral in this case. So using this definition, we'll go ahead and write this as a big old square root, and then the averages 1 by 1. Actually, let's just work out the averages 1 by 1 first. So Vx squared average. Now we are allowed to distribute an average over a sum. It is linear, but we just can't pull it outside the square root. So this will be 1 over, now again, I'm talking about time averages here. So the time I'm interested in is from time 0 to time, maybe I'll call it t over 2, where t is the total flight time of this projectile. We've worked that out before. The total flight time is 2 v naught sine theta over g. So half of that will just be v naught sine theta over g. You could also just sort of say, yeah, it's the time it takes until the velocity is 0. And we'll start from time 0. And then when we square this constant, not much interesting happens, right? That squared constant will come out. This t over 2 thing will just sort of cancel off the t over 2 that we get here. And of course, the average of a constant is the constant itself. Nothing difficult there. When we go to the y component, though, and I find its time average of the square, we still are integrating over this interval. But now when I square this, there will be some non-trivial integrals to do. So I'll go ahead and write this 1 over t over 2 as this thing flipped with an extra 2. This thing, when we expand out the binomial, won't be too hard to integrate. And then we just have a constant, a linear term, and a quadratic. So polynomial power rule easy. Okay, so here's our final result. I suppose we could actually simplify this because t over 2, which is this factor out in front, at least inverted, can cancel 1 power of each of these t over 2's in each of the terms. Then we do just have to plug in what t over 2 is in each of these cases and try to simplify. Let me go ahead and bring that up to the top of the next board. Okay, so here's what we get when we simplify that down. And by the way, probably even easier technique would have been to just make a u sub of that, this whole thing being your vy, because it's in the square, it's a linear term, and then you don't have to expand out a binomial. It's a little easier. Anyway, they both do reduce down to something pretty trivial. We are not surprised to see that Vx average depends on cosine and Vy average depends on sine. What's weird is this extra 1/3, and that's because of that GT term changing with time. So it's not a constant, it's a little bit smaller than you'd expect because we start off with whatever that initial value is, but then eventually we get to 0. Putting these together, we find that our RMS speed, which is not the same thing as what we're actually trying to find, will just be the square root of these added together. I'll go ahead and pull out the V naughts from the root, but we are left with this result. So it does depend on the launch angle. If you want, you can go ahead and rewrite this, like replace the cosine squared with 1 minus sine squared. That's fine, it's up to you, but we do have something that depends on theta. So let's save this off to the side, and then let's go about actually trying to find the average itself. Okay, so over here, I gathered up our first result that the RMS speed, I went ahead and replaced that cosine squared with 1 minus sine squared, has this form. And notice that's the square root of the average of the square speed. We want the average speed itself. To calculate that using our usual rule, okay, I'm still going to be looking at the same interval, but the function I'm actually trying to evaluate is the speed. which is the square root of the sum of the squares of the velocity components. So now notice the root is on the inside of the integral, unlike here where the root came after we did our integrations. And that makes all the difference. Now in this case, when I add these together and square them inside the root, it'll be a little messy, but we can do some usual sort of trig substitutions to make this simplified. So let's go ahead and pull the Vx, which is a constant, outside of this. That'll just be a little more convenient because this whole thing in parentheses is a linear function of t. So if I let a u substitution come in where u is equal to all that junk, call this u, then we'll also have that du is simply minus g over this v naught cosine theta. Cosine theta. dt. That means that our integral, I'll plug the t in later, when t equals 0, my u just becomes sine over cosine, which is tan theta. And when t equals this capital T over 2, I can use the fact that the velocity in the y direction there is 0. That's kind of how we defined this halfway point. So the whole numerator of this will be 0, which means u is 0 at that point. So that's kind of convenient. I don't have to go through all the plugins for that. We still have this bit out front. It's going to cancel with this. We have a square root of 1 plus u squared. My dt, oh, sorry, I guess it won't cancel. It's going to double up with this. My dt will pick up a negative v naught cos theta over g du. I'll use this negative to flip the order of my integration. I'll pull the v naught squared cosine theta out to the front, and I'll go ahead and plug in what my t is while I'm at it. So what will that give us? We'll have a 2. This g will come out, and this 1 over t will cancel it off, so the g's will be gone. I will be left with a single v naught, and then I have a cosine squared from both of those, the v naught squared partially canceled here, over sine. Okay, that just leaves us with this integral to do. We could do this integral right now if you'd like. It's just going to be a trigonometric substitution. So u, I would choose to be something like tan phi, so that du is going to be secant squared phi d phi. Notice that when I do this square root, 1 plus tan squared is going to be secant squared under the square root. Then it'll also pick up a secant squared here from the Jacobian, and that will give me a secant cubed. When u equals tan phi, we can see that phi is just going to go from 0 to theta. And this trig substitution, or rather this cubic secant function, is kind of a famous integral to have to work out. It's a little tedious, so I'll spare you the details. You could use integration by parts, or another sort of trig substitution to undo this. I'll just write the result at the top of the next board, and then we'll see how that compares. Okay, so here it is in all of its sort of messy glory. We do have the cosine times cotangent is that cosine squared sine, or sorry, cosine squared over sine that was out in the front. It canceled off some of the stuff that came in the result of that integral. This natural log does show up when you do that integral. By the way, there's another way of doing that integral instead of using a trig substitution, using a hyperbolic trig substitution, or you can rewrite this in terms of an arc hyperbolic sine. That works too. You can trade out the log for that. That's okay too. In fact, previously we've actually worked out what the length of a projectile path is based on theta. And so you could look at the average speed as just being length divided by time. So if you go back and look at that, you could think of this as my average speed is just going to be half the length of my parabola divided by half the period of my parabola. And since we had already worked out what the length of this parabolic arc is, which did involve either natural logs or the inverse hyperbolic sine, we could have gotten it this way with no additional integral. So notice, this looks a lot different than this. We do see a dependence on theta, of course, but and this should have had a V naught attached to it. But we do see that it's a very different functional form. To finish off, let's actually look at one other type of velocity average that you might want to calculate that's, again, closely related but not quite the same as the average speed or this RMS speed. And that is, let's take a look at the magnitude of the average velocity itself. So that's different than this. It's also different than this, right? This is the average of the magnitude. What about the magnitude of the average? So for that, it's not too bad. To calculate these, I'm thinking of needing Vx itself. That's the average of the x component of the velocity. And then I'll need the average of the y component. This is a constant, so I don't even need to do any extra work. The average of the y velocity, we could go through the integral and do it just like we did with Vy squared. But actually, let's just take a shortcut. We know that Vy is a linear function of time, which means it starts at V naught sine theta and it ends at 0. So the average should just be halfway in between. It is a linear function, so we can just make a quick sub and say it must be half of the difference between the initial and final. You could, of course, do the integral to prove this. Now, when I want to find the magnitude of the average, that'll be the square root of the average of the x squared plus, I should say it this way, square root of the average of the Vx component squared plus the average y component squared. And when we square these and add them together, again, I can pull out the V naught, and I'll be left with a cosine squared plus a 1/4 sine squared. And just to put a comparison with this, we could make the cosine squared equals 1 minus sine squared substitution, and we'll get 1 minus 3/4 sine squared theta. So collecting everything over here on the right, we can see that this RMS speed, which is one type of average, is V naught root 1 minus 2/3 sine squared. The magnitude of the average velocity vector itself is V naught root 1 minus 3/4 sine squared. And the average speed, this result here, I'll rewrite it in a slightly more condensed form because I'm at the edge of my board, is V naught over 2, 1 plus cosine theta, cotan theta, arc sinh of tan theta. All three of these are various versions of average. The one that this problem is actually looking at is the average speed. That's this last one. But there are a couple other versions we might talk about. And it should be noted that all of these results, we're thinking about the average over time. Maybe in a future video, we'll look at what about the average over height or the average over x. At any rate, we have our average velocity, rather our average speed, at various different launch angles and a couple other related average quantities. QED.